All right, lesson set 27, full screen. I don't know if this is about the third or fourth time that we've tackled the same material, so hopefully we're emerging from the following stage and we're getting to the do-it-yourself stage. At least that's the hopeful transition. Let's bring Renee this way, center this up a little bit. Rational functions, fractions can be big, they can be small, positive, negative, zero, undefined, all those things. So let's go after it. As they get more complicated, very helpful to put things in factored form, right? This quotient as a division of products. And so let's have at it. What can we see immediately? I can see immediately that it's going to zero on the right. We've talked about this exponent bigger than that one. And so those are the big players, which is going to give us a 1 over x. And as x gets bigger, that fraction gets smaller. Math builds on itself. If you don't know how to factor x squared minus 25, the difference of two squares, or if you didn't know that there's a plus minus square root of 25 when you set this to 0, then you wouldn't be able to write quickly an asymptote of y x equals 5 on the right and 1 on the left. Once I've established those values, I can estimate 1 to be about there. That's my guess. What else can I see immediately? Negative 6/25. Negative 6/25. Do I want to put it on the right or the left side? That's a tough one. Let's hold that in abeyance. 0 gets us minus 6 over 25, which is around a fourth. So it's going to be about there. I know I'm going to get sign changes everywhere. So this is going to go from positive to negative, to positive to negative, I believe. But more analysis will bear that out or tell me that I'm wrong. I had a good chuckle this morning, Yasser. Now that I'm thinking about the t-shirt comment, had a good chuckle. All right, I'll come back at you at some point. All right, what do we got next? We got as x goes to 5 from the right. Why don't we check that out? See if you remember what that means. All right, I'm going to pick a number like 5.01. And that's going to be slightly bigger than 25. And I can make that this much bigger. All right, so I got a really small number that I'm generating here. And if I put 5 in here, I think it's safe to say I'm near 21. Well, that looks to me like we've got behavior, numerical trajectory that looks like that. Let's prove it by putting a 6 in and seeing that we get a relatively small positive number, certainly nothing like positive infinity, which we just answered numerically. And I think if this is correct, graphically, if we had the graph, we could just follow the, from 10 to 9, 8, 7, 6, 5.5, 5.1111, 5.01, which is what we did here. All right, you got to work with numbers. And I got to work with an eraser over here. And I'm not going to be in any rush to do anything. And maybe I'll cut down on some careless errors here. I'm not under any time pressure. All right, so what happens when we make this 4.9999999? We get a sign change. We get the same thing, but with a negative. So we're going to negative infinity. Boom. And it would be nice to justify that with a user-friendly number like 4. So that's going to get me 12, roughly, let's see, 12 plus 6, 18 in the numerator. 16 minus 25 minus 9, so minus 2. So 4 gets me minus 2. So I'll might as well make this a little better. All right, so there we go. 4 gets me minus 2. And then we can anticipate that this is, doesn't look like it's going to change signs here, does it? 1, 2, 3 changes. 1, 2, 3, 4 changes. Yeah. Oh, I haven't looked at the x-intercept yet. That answers that question. So the x-intercept is -2. We'll put that right about there. All right, so let's do this again. So it looks like something like that, which would mean I'd have to move this number here. I forgot what we had, but it was in this vicinity. So I'm getting a little better shape to the graph, and then it's got to do that. And then it's got to do this. And I'm basing that on sign changes, which we're going to develop during the second half of the term. But let's verify. As x goes to 5, okay, well, I'm going in different directions again. Can't be at the same place at two different, can't be different places at the same time, so to speak. We say that does not exist, DNE. Okay, and what am I missing over here? End behavior goes to 0, right? The bigger the number I plug in here, the more this happens. The bigger that number gets, right? We're looking at the major players. We're not looking here. We're looking here because I think when you put a billion in, a billion squared has a lot more bearing on the sum than +6 or whatever it was, -25. All right. We can verify this again by plugging in maybe -10. So let's see, I think it was +6, -25, -10. So -30 + 6, -24, -10 squared is 100 - 25, 75. That's a very small, maybe it's close to a third, but it's negative. And I'm picking a number out here. So you have to plug numbers in, right? And not plugging numbers in is just being a little lazy, right? Especially when you're learning how to do these. The sooner you plug some numbers in, the sooner this causes less trouble. All right, so I hope I got us at least looking at another rational function. X-intercepts, y-intercepts, asymptotic behavior. Sine of 11 pi over 3, -√3/2. We want to be able to do that quickly, unless I'm missing my coffee. I got the shirt on right today, so maybe I'm okay. So I want you to have a feel for this as in a radius length, right? We're going to start at 0, go around the circumference of the circle. We're calling this a unit circle. Every radius is 1, doesn't matter the size. I could have a smaller circle here. I start here, go around 6.28, whatever that distance is, 6.28 takes me once around, whatever that distance is, 6.2 of them takes me around the bigger circle. So let's get that out of the way. So I did throw this into Google. I typed it in 11 pi over 3 so that the distances are now a little more accurate. I was just estimating without a calculator a little while ago, but we'll put these in and some good stuff comes out of it. 0.52 radius lengths opens up to about a 30-degree angle. So if this was the radius, 1, here's 1 unit of radius length, boom, 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 that distance. And if I cut that in half, we start to see the 30-degree angle materialize. All right, so we just want to keep these conversations going. Now, what I did to estimate this, because I like to estimate the answer before I actually do this type of calculation. I like to look at that number and say, well, where is that on the circle? Well, here's 6.28, here's 4.71, 6 and 4 is 10, add those up and you're at 10.99. And we got to go another 0.52. Ah, yes. So nice connection to be made. Another 0.52 is 30 degrees here. So that puts us at that triangle. Now, if we're doing it from the standpoint of exact values, because you don't need a calculator for this, pi is the top half of the circle. That's what we've been doing. Good drawings get good answers, breaking it up into 3 parts, dropping a perpendicular, and that right there should be 1/2, and 1/2 gives me 1 unit to the right. So hopefully that looks good. Okay, hopefully that looks good, that distance, 1/2. And then we've done Pythagoras enough. √3/2, approximately 0.87 for a height. Radius is always 1. But where are we? Where are we? Well, hopefully we can cut to the chase and say, well, that's 12 pi over 3. That's twice around. I'm at 11 pi over 3. Boom. And that's what we want to do next, is get right to here to answer the question. All right, so that's what that answer was. Now we're going to do the cosine of -pi over 3. Ah, again, we're hitting minus 1.05 radius lengths. Minus one, a little bit more than one. A little bit more than one radius length. And that's going to take us in the general vicinity of here. Yeah, that's where it's going to take us. Of course, starting from scratch again, pi, top half of the circle. But we're doing what? Going in the other direction. So we want the bottom half of the circle. We're going to break it up into three parts. Aha, coterminal. Minus pi over 3 is exactly the same place on the unit circle as 11 pi over 3. Interesting. So we have exactly the same triangle, right angle, hypotenuse 1, cosine a half. So that's the answer to this one. But I'm hoping we get a little feeling for where we are on the unit circle. Because I've asked this now for, I don't know how many times, the sine of 3, and I'm hoping that at some point we get some recognition as to what I'm asking. Where's 3? There it is. Draw the triangle. What do you notice? The height and the arc length are almost identical. And that's why we can say 0.14 without a calculator, to get a feel for the calculation. All right, tan of 11 pi over 4. 11 pi over 4 is about 8.63 radius lengths. All right, so where is that? Where's 8.63? Well, this is 6.28. I know this one here is 1.57. So 6 and 1, 7. So I'm a little more than that. I know 3.14 is here. If I add 3.14 to 6.28, I'm at 9.42, 9.42. That's too far. So I'm somewhere in the, the second quadrant, but going around that many times. First, second, third, fourth. I suppose you could talk about fifth, sixth, seventh, and so on and so forth. But let's cut to the chase. Let's cut to the chase. We're getting a feel for this, hopefully. This one, getting a feel for it. But now we're going to do it how? I'm going to draw pi, which is the top half of the circle. I'm going to break it up into 4 parts. So that part first, then boom, and I start to get a good feel for a 45-degree angle. And I want to go to 11 pi over 3, and I know 12 pi over 3 is here. Oh, 11 pi over 4, excuse me. I keep losing track of where I'm at. 11 pi over 4 is pretty close to 12 pi over 4, which is 3 pi. 1 pi, 2 pi, 3, which is here. So that's coterminal. 3 pi is coterminal to pi. That's same place. So 11 puts us there. We know it's 45-degree angle. Starting to get familiar with negative root 2 over 2, positive root 2 over 2, trying to get a look at those 45-degree angle situations. You can do Pythagoras if you're not sure, x, 1, right? So 2x squared has to equal 1. X squared equals the square root. Since it's distance, I'm not going to say plus minus 1/2. And I want you to know that the square root of a half is the same as root 2 over 2. You've heard it. You might have to hear it a half a dozen times, and then maybe it'll be part of your working vocabulary. All right, so that answer was, never did answer it, tangent, height over width in the unit circle, so -1. Okay, do that 3 or 4 days in a row and you'd start to get the hang of it. At least that's what I've seen over the last 45 years. Again, height in the unit circle, the sine function is the height. That's the sine of the angle. X stands for an angle. The sine of the angle, the cosine of the angle, if we're in the unit circle. 0 to 6.28, 1 revolution. We want our heights to equal -1/2. Where does that happen? Well, let's get the unit circle again. Let's go to a height of 1. Let's go to -1. Right down the middle is 0. I think halfway is about here. We draw the triangles. And we start to get a feeling, I hope, for that angle, 30 degrees. So that's a -1/2. That's what we wanted. This one's -1/2. That's what we wanted. Okay, so are you getting familiar with pi over 6? 1, 2, 3, 4, 5, 6. Are we getting a feel for that being a half? Root 3 over 2, 0.87, right angle 1. But It's not happening here, it's happening here and here. 1 pi over 6, 2, 3, 4, 5, 6, 7. 7 pi over 6. Let's see the sine function. 1 period. 30-degree angle past 180. Does that look like we're down halfway? I hope so. And then again, it picks it up there when I'm at that one and also this one. I'm 30 degrees from 360. Does it look like that might be 30 degrees from 360? I hope so. So 7 pi over 6 and 11 pi over 6 is how you do that one. All right. Now, what's the quick way to find the period of a function? Take the multiplier and x over 3. The multiplier of x over 3 is 1/3. Right? 1/3 times x is the same as x over 3. So there's my multiplier. I divide it into 2 pi, and I now know from start to finish is 6 pi. This period is going to be 6 pi, and it's a sine function. So we'll start at 0, measure heights from 0, all the way to 90 degrees, back to 270, back to 360. And now we have 20. Oh, okay, well, we're going to see the 6 pi materialize here. So 20, 25, 15, range 15 to 25 for this function. It starts at 0, 6 pi later, because I'm dividing by 3. That's 1 revolution, coche. I'm back to 20, which means 3 pi should be 20, and 3 pi over 2. 3 pi over 2, which is 270 degrees, which if you divide by 3 is 90 degrees, and 90 degrees is the maximum you get for heights in the unit circle, and sine function measures height in the unit circle. So if I divide this by 3, it means putting a 3 there, that cancels, I'm at pi over 2, the sine of pi over 2 is 1, times 5 is 5, plus 20 is 25. I'm hoping you're getting a chance to see how those numbers work. Yes, I wonder how you could tell me what the period of this function is. The sinusoid, cosine, very similar to the sine function, just 90-degree difference. Oh, there's the multiplier. I can take the multiplier, divide it into 2 pi, and get pi over 2. Now, why can I do that? Why can I say that 90 degrees is the period? Of course, if I multiply by 4, it's 360, right? Well, I got to look at the start. That measures angle. I want to know when it's 0, when I start my walk around the circumference, and that does appear to be at 3. And then I go, and I come all the way around. And that's going to become 3 plus 6 pi, plus pi over 2. I'm doing the last problem in my head. Okay. Yeah, I guess that's it, because I solved this for not 0 this time, but for 2 pi. So let's see what happens. Well, I think I can bring the 12 over, and I think I can divide by 4, both of them. 3 plus 2 pi divided by 4 is pi over 2. Oh yeah, I get that. So if I knew the start, and the start is going to be 0, and 0, cosine is 0, guess we got to draw a circle. Cosine is 0. Cosine measures width. Width in the unit circle. Well, that looks like a max. So I think 0 gets me a max, then the shape that I want is max back to max. And I'll start at what makes a 0, in this case is 3. And if I knew pi over 2, I wouldn't have to do this. No, I could just say that, well, I moved pi over 2 from 3. I think I'm at 3 plus pi over 2. Boy, that would be a little quicker. And what's the midline of this one? 6. Might be different on your sheet. Up and down 10. So if I go up 10, I'm at 16. If I go down 10, I'm at -4. Oh, that's okay. So let's look at pi over 4 here. 3 plus pi over 4 should get me -4. So let's do that. Let's put in 3 plus pi over 4, parentheses, minus 12 plus 6. Okay, well, I can see 4 times 3 is 12 minus 12. That's going to cancel. I see the 4 is canceling. I'm at pi. There's pi. So I wonder what the width is there. I think it's -1 times 10, -10 plus 6, -4. Playing with some numbers here. All right, I decided to represent volume as dimensional cubing. All right, so now let's go back to g of x. All right, so let's change that. Let's change that. Let's change that to the more familiar situation. But remember, we're working with dimensions and we're working with volume. Boom, boom, working with cubes. And what do we know about perfect cubes? That they come from the average of the roots, and that's minus b over 3a. And that's where the point of inflection is going to occur. So what do we have here? Let's do c minus 3ah squared so I can get shape immediately. C2 minus 3a is 2. I got to find h, which is minus b over 3a. So minus 18 is 18 divided by 6. So I now know at 3, that 3 squared is going to give me the rate of change. And it's negative. I can see it's negative. So I now know I'm doing this. All right, what else do I know? I also know that 3 is here. 0 gets me 5, and I'm going up at that instant. So there's my tangent. There's my tangent to the y-intercept. It's 2x plus 5. Okay, you would have had to have seen other earlier videos, and some of you aren't looking at them. I know. Santa knows. I know. I have something called a computer and a program in our grade book that tells me what you open up for the videos that I assign. Oops, some of you just took a hard swallow. All right, so therefore, I'm going up at 2 to 1. So I now can find my x value for the local max. And that x value is 3 minus the square root of, I guess I got to do this now, 9, 18, 54, 2 minus 54 minus 52. So now I know that that's 52 divided by 3 times that is 6. And if you do that out, it should put you just to the right of 0. And over here, I've got x plus x equals 3 plus the square root of 52 over 6. How did I know that? Well, that's a good question. I got to go back to the 1990s. Pre-calculus, that's for sure. So those values come from minus b over 3a, which I'm going to call h, plus and minus the square root of opposite of m. The rate of change at the point of inflection is down 52 to 1. That's what's going on there. It's the interplay of the rates. So we take the opposite of that and divide by 3a, and a in this case was 2, and it was that quick. Okay, so one more time. H plus or minus the square root of minus m over 3a. Yes, you have a little bit of memorization, not a whole lot. And what is m? M is c minus 3ah squared. And if we do that every day for 2 minutes, in a week's time, you should be able to remember it. You should be able to work with it. And then if we do it until May 15th, you might even remember it when you go to your next class. All right, so I got to put 3 in to find out where I am. So minus 54, so that's positive 54. Which means that this is twice that, and 3 times it. It's 150 minus 162, 2 times 3, 6 plus 5, 11. All right, so this becomes twice that, minus 108, minus plus 11, so I got to take 11 away from that, 98, 97, I believe, minus 97. Hope I got that right. I got to check from Yasser. He'll tell me if I did that right or not. Hopefully I did. And there's our local max x value, local min, rate of change at the point of inflection. Putting this in graphing form for you calculus folks. The equation of a line tangent to the point of inflection is a very famous problem in calculus. Everybody has to do it. And so there's your tangent to the point of inflection. And all you needed to do, whether you realized it or not, was to put a 2 here and an x minus 3 in cubic, and you got the graphing form for a cubic. All right, rough around the edges on those first conversations, and I don't worry about that too much because we're going to be doing it for weeks, and I'm not grading you until May 15th. You just got to show me that you can work with this. All right, variation. Y varies directly as x, direct. So y equals kx, we just substitute 12 for y. Find the constant of proportionality. We got a 4, so we can now see that k is 3. So we go back up here, we plug in a 3, and then we find the missing variable if x is 6, so therefore y is 18. Okay, we're basically doing the same process, but instead of direct variation, we're going to do inverse, which is y equals k over x. K, we're looking at x is 10, so we got k over 10 when y is 3. So it looks like k is 30. So therefore, I make a 30 up here. I switch my x to 60. And I can see y is equal to a half. That's kind of the work we're doing. All right, enough said there. This is Algebra 1 review. Got a feeling it's new for you. Joint variation. Y equals k, y varies jointly. Still write it, the first 3 things the same each time. Where was I? X squared and inversely as the square root of z. And then give you some x, y, z values and you can manipulate them. All right. Moving right along. Let's see, we got ln of 25. Can you do that in your head? Approximate it. Hope you're saying 3.2. All right, you can approximate pretty closely as long as we're on e to the x locally. As soon as we get into where a little change in x causes a great change in y, this isn't going to help us much. But in terms of helping us learn to graph e to the x, learn to graph ln of x, very useful knowing some local numbers. And I've asked you to tell me e to the x equals 5. What is that x? It's approximately 1.6. That's what we're working. So what's 25? 25 is 5 squared, which is e to the 1.6. That's 5 squared, approximately. There's your 3.2. Hoping you can do that quickly. A lot of you I now know can do that very quickly. I'd like to get the entire class doing that. So now, what do we have here? We have the ln of 5 squared. I think that was part of the discussion we had over here. And I think that that is the same thing as ln of 5 times 2. That's an exact answer. I think that's what we did. I think we changed 5 to e to the 1.6. And I think we did 2 times 1.6. And what is 2 times 1.6? Exactly what we were approximating here. So I'm hoping you can see the rules of logarithms. Okay, so what's another name for ln of 8? For instance, ln of 8 is 3 times the ln of 2. Because 8 is 2 cubed. And what am I doing with the exponent on top of e after I change a number into e notation? I'm multiplying it. I'm multiplying that exponent. That creates the base that we need. Okay, I hope I'm getting a little better with the language there, but time will tell. So there's using rules. So the ln of 5 squared is equal to 2 ln of 5. Okay, that 2 could go here. And then we can move it there. All right. We'll keep talking about it. Powers and roots. Oh, so 3.2. What is that in terms of powers and roots? What's 32 divided by 10? That's an exponent. I think we're doing something 32 times and taking a 10th root, and I think we better get a calculator. I don't think we're doing that in our head. All right, another rational function. You've had a chance to forget how to do it because we did it 20 minutes ago. So what do I see? I see an asymptote at 5. X equals 5. I see that we're going to 0 again, because as that gets bigger, the fraction gets smaller. And so we've got one sign change. I see -6/5 for the y-intercept. I don't see any x-intercepts. I just don't see any. So it's going to do this. Unless you can tell me how I make that 0. Again, we have to make the numerator 0. And if you see that 6 turn into a 0, give a call. Yep. Who are you going to call? Oh, I'm dating myself. 5 from the right, I'm going to positive infinity. Let's just use the graph now. 5 to the left, negative infinity. I'm just following the graph. As x goes to 5, does not exist. The limit does not exist. And repeating a lot here. Repeating a lot, but hoping that you can check these things with what? If you're not plugging in numbers, you're not gonna see that materialize. You gotta throw some numbers in there. Let's throw 100 in there. 100 minus 5, 95. 6/95. I hope you say that's a small positive number. Let's throw a number like 6 in. 6 minus 5, 6 gets me 6. It's on that trajectory. Do the same thing with the negatives. You got to put some effort in. All right, mixture, candy mixture. 20 pounds at 80 cents. That's our final destination. We want 20 pounds times 0.8. We got our first batch at 60 cents. Let's call that 0.6x. Our first batch is x, and our total is 20. We talked about this the other day. If this is 20, and I take away 5, then that's 15. If I take away 6, that's 14. If I take away 7, that's 13. If I take away 8, that's 12. If I take away x, that is what? 20 minus x is what your brain was doing. Well, we got a batch, a certain amount of that 20 pounds, x, and then we want $1, which is 1, right? 100 cents. So why don't we do it as 60 cents? Let's do it that way, get rid of the decimals. 100 cents times what? 20 minus x equals 80 cents, right? And I think that's all we'll do is write the equations from now on. Just set up the equations. If you're going to go up the ladder, I got to assume you can do that right. All right. Okay, so Q, quadratic. I decided to use the letter Q for quadratic. 2x squared minus 20x plus 7. We're going to use rates of change. Okay, so come on, Renee, let's go over and look at our rates of change for quadratics. It's a handout, should be in your notebooks, and now we're going to use it. All right, so what do we see? I see an average rate of change. I got to get that on the lesson sets. You're going to see that average rate of change is over a decent interval. What's a decent interval? Who can say? What's a small interval? 0.01, I'm going to say. All right. So 9410, 149. Here's the numbers that go with the change at each moment. Gives us a feel for a momentary change. Minus 3.001 to minus 3 is a change of 0.001, and it's negative change. That's a smaller number than that. So 5 is a smaller number than 6. 5 to 6, 1 unit of change going up. So that's what I meant to say, going up, right? From this one to this one is down 0.006, right? I'm going down 0.006, going down 0.001. I'm going down at 6 to 1 at this instant. There's 6 to 1. Minus 2, 2, 2. It's easier to look at the positive numbers, right? 0 gets you 0, 0.01 gets you 0.0001. And if I do 2 decimal places, it's 0.00 divided by 0.01. Well, that's 0. And I'm flat at 0 squared. That's what the graph of that quadratic looks like. It's flat there. And then if I move over to 1, 1.01 gets me 1.0201. That's going up at 2 to 1. At 2, I'm going up at 4 to 1. At 3, going up at 6 to 1. That's the rate of change of x squared. Its rate of change is what we call a derivative, right? It looks like I'm doubling the x value. And there's the picture we're going to be working with, especially this one. So if I go up 0.01, just 0.01, I get a new layer of area. A new layer of area, and that's what these tables are representing. I don't expect you to pick that up in one day. Newton came up with this in the 1600s, I believe. And that's not that long ago when we talk about the history of mathematics. People were adding and subtracting a lot earlier than that. So this is fairly new on the evolutionary scale of the discipline. I fall on that side of the coin. I think it's evolving. Okay. And I'm going to keep playing with this for the next 2 months. And hopefully you're going to follow why I'm doing it, and it will help you in future classes. So I now know that x squared, the rate of change of x squared is 2x. There's x squared, it's 2x, and I'm doubling it. Well, if I went back over there and doubled all those values, you'd see that the change is twice what it used to be. So we'll just use that symbol, derivative symbol. That's going to represent the rate function. X squared is changing by that, and I'm multiplying it times 2. Linear functions are always, this one is always going down 20 to 1. If I go down if I change 1 unit here, then I'm going down 20 units here. Right? Rise over run. And it doesn't matter if this is 0.1, then that's 20 times that, or 2. Just moving a decimal place. All right, so that's our rate of change. That's constant. And we know that in a quadratic, the vertex has a slope of 0 right there, has a tangent. So when does this equal 0? When does 4x minus 20 equal 0? When x equals 5. Now, how have we been getting 5 from this? Minus b over 2a. Positive 20 over 4. There's the 5. Our old-fashioned way. This is another way of looking at it from a different perspective. So that is my rate of change for this function. And what happens if I put a 0 in here? 4 times 0, oh, I get minus 20. Wow. So I now know that I have a cup shape up. And I'm not going to explain that. I'll do that the next time we look at that table, add that to the discussion. It's the rate of change of the rate of change that we'll look at. And if it's positive, I have a cup shape that's up, a slope that's 0 at 5. I know the tangent. If I put 5 in, we find the y value the same way I always did, minus 100, minus 50, plus 7, minus 43. And I also know that the y-intercept is going down at the y-intercept. So I'm on this side. 0 gets me 7. And I'm beginning to use rates of change to study a polynomial. All right. Of course, now once I have that, I got the roots and everything else for previous levels of study. I'm going to do this graphically. I've got a root at -2, and it's an odd power, so I'm going to use a dashed. That's an odd power at 5. I've got a dash, and I've got a dot at 0. I'm not going to get a sign change there. So let's look at the sign changes. Let's get this out of the way. All right, let's do sign changes. Let's pick a number bigger than 5 to see if it's true or false. And then I'll do the graph as well. So bigger than 5, 10. 10 gets me a positive, 10 gets me a positive, 10 gets me a positive. I'm going up. True, bigger than or equal to 0. I know that a 4 is going to be false. 4, positive. 4, oh, I get a sign change at 5. 4 minus 5 is negative. 3 times 4 plus 6 doesn't affect that parentheses, doesn't affect that one, but it affected that one. And if that's a product, that product is not greater than or equal to 0. False. I know it's going to stay false. Let's put a 0 in. 0. That's, I don't want to put a 0 in. Let's put -1 in. -1 squared, that's always positive. I don't care what number you plug in there except 0, it's going to be a positive. So that stays the same. -1 minus 5, that stays the same. -1 times 3 plus 6 cubed, still the same. The same. If it was false, it's still false. And then I know it's going to be, well, it's going to have a cubic look to it. I know that the graph is going to have a cubic look to that intersecting point. But there's a sign change, so it's going to be true. Let's pick a number less than -2. How about -1,000,000? Well, that's still positive. -1,000,000 minus 5, that's still negative, but -1,000,000 times 3. That's a negative parentheses. And a negative times a negative times a negative, I get a sign change. And a negative times a negative is a positive. So that's what the graph looks like. And so what's my answer? 2 greater than or equal to 0? Well, from -infinity to -2, these are positive values. From -2 to 0, they're negative. From 0 to 5, they're negative. And bigger than 5, they're positive. So I don't have any room here, but -infinity to -2. And remember, -2 can work because I said or equal to, so we'll use a bracket. Union, 0 works. Union, that does work. Put a 0 in. 0 times anything is 0. And 5 to infinity. And I'm losing my breath. Now, how are we going to do domain? Exactly the same way, except we're not going to graph it. We're not going to graph it, but we are going to say, yes, we can use, or no, we can't. Based on what? Critical numbers. 9 is a critical number. 0 is a critical number. So is 1. Because the ln of 1 is 0. The 3 functions that we're going to most work with at this level are the square root, logs, and division by 0. Those are where they're going to restrict what numbers we can use. Okay. Square root, what do I need inside? Inside. The square root has to be greater than or equal to 0. Inside the parentheses has to be bigger than 0. Division by 0 is not allowed. So why did I put a 1 there? Because the ln of 1 is 0, and I can't use that. So that's restricted. What makes this positive? X value is greater than 0. That's restricted. I can't use 0, but I can use these numbers. Yes, I can use those. Can I use the numbers between 1 and 9? Pick one. Can I put an 8 here? Absolutely. Can I put an 8 here? Absolutely. Can I use 8? Absolutely, yes. Can I pick numbers bigger than 9? Let's plug one in. 10. Whoops. Square roots and negative are not going to show up on Rene Descartes. No. Can't use negative. So what was the domain? From 0 to 1, union 1 to 9. Can I use 9? I can use 9 here. Can I use it here? 9 minus 9. Can I do 0 divided by the ln of 9? Absolutely. That equals 0. So can I use 9? Yes. So I have to amend this to be a bracket. All right. Now, I think I might have had one more question. Oh, sine of 19. Sine of 19. Approximate sine of 19. Well, that's got to have some meaning for you. If that doesn't have meaning for you, sorry, can't do the problem. So I'm hoping you recognize this as walking around the circumference of the circle, 6.28. I want to get to 19. Why don't I multiply that by 3? And if I do, I get a 4, I get an 8, and I get 18.84. Wow. How far is that from 6.28? 18.84. Where would that be? Well, 3 times that, 18.84, 3 times around, yes? So I'm here. That's what that is. And I got to get to 19. 19. So I got to go up 0.16. I got to go up 0.16. Hope I'm not making a careless error here. At least I got the shirt on the right way today. All right, so I'm saying it's approximately, how about 0.159? And then I got to go to Google and see how close I was. All right, hope I didn't botch that at the end. All right, so that's my guess. Just trying to get a feel. So type that into Google, see how close it is. I know I'm gonna. All right, running out of breath here. Early morning still, but nice day. And I think what's gonna be one of the last cold days, I hope. Gonna be warmer tomorrow. All righty. And then I'll put, this was lesson 27. I'll do 28 later today and put it up tomorrow. And if you're practicing each day, each problem, a couple minutes each day, after about 4 days, I'm hoping tomorrow's lesson set, you look at and you go, I'm starting to pick this stuff up. And then we'll just work with everything we've done so far. And it's about 120 problems maybe. We'll see. All right. Toodaloo.